Hi. So uh, I am going to tell you the six properties of the divergence curl and uh, uh, and the gradient two of each. But before that, let me tell you one thing. So we have a scalar, let's say f and g, and we have a vector, let's say a and b. How can we merge these two things? Either we can what we can do, take the product of two scalar, or we can say take the product of a scalar and a vector, or more what we can do, we can take the dot product of two vector, okay, or we can take the cross product of two vector, okay. Is there any other way we can just combine these two things? No, these are the different way we can combine the scalar and a vector. So we what we are going to see that these combination will form the different formulas that we are going to see now. First we will talk about the gradient, okay. So a gradient operate on a scalar function. So what are the scalar function? Only this function and this function is a scalar function. So the gradient will operate on this function first. Let's name it 1, 2, 3 and 4. So the gradient will operate on only 1 and 3. So let's see the first one, okay. So what is final result? Remember, this del operator is exactly like this ordinary derivative for one dimensional case. So the way this ordinary derivative works, the del operator in some sense works exactly same. So this is going to be, so how we you should remember this product rule. V and W is nothing but V times dW by dx plus dV by dx times W. So in the similar way, this formula will give this result. Okay, so this is the first rule. The second rule uh, is the second formula is for this third condition. Third case. Okay, so del of A dot B. So what is it? Well, it's a long complicated formula, so let me write it. A cross del cross B plus B cross del cross A plus A dot del acting on B plus B dot del acting on A, okay. So this is a little bit complex formula, so let me explain it. Okay, so first of all, this first formula can be proved by expanding this del operator, and okay, so let me just give you a hints how we can prove the first formula. So we are taking only two component. We can always expand for the third component as well, okay. So what we can do now is f and g we will use. So this is the partial derivative, so we will use the product rule over here, the product rule for derivative. So once we expand this, so after expanding this we will get x cap. In the similar way we will get f g of, in the similar way we will get the other term. So it can be always written as and the other term. In the similar way, we can write f del of g. In the similar way, g del of f can be also figured out. So in this way we can actually prove the first one. Now let's come to the second one. So first of all I'm removing this so that I can do it just below our formula. I'm removing this and pushing it downward. Okay, so now let's come to this formula, the second formula. Well, from the tensor analysis we can easily prove this identity. Okay, so first of all let me explain you something. So the dot product of a dot b, and it will give you a scalar, and the scalar the gradient will be taken of that scalar quantity. Okay, so what is its formula is actually the curl of the first one of those function, let's say b, and taking the curl with the first function. In the similar way we will replace a and b to the first formula. In the first formula we are replacing the first a and b, then we will get the second term. Okay, these two things are totally different. Okay, so a dot del of b, how they are going to look like. Okay, this a dot del, how we are going to write like this, ax del by del x. Okay, ay del by del y, and the other term. Okay, and which is acting on b. So this final result is del by del x b x plus. Okay, so what we are doing over here, so we are expanding this b as a bx x cap plus by y cap. Okay, so we can write like this, bx x cap plus by y cap. So there will be, so this is not a dot product, these and these are not dot product, it is a scalar quantity and it is a vector quantity. So what we will get, there will be 4 terms bx. Okay, the first will act on this, the first will act on this as well, because this is not a dot product. Remember this, there is no x cap, so that it will take the dot product with x cap and the answer will be 1, and then this x cap will be dot product with y cap, then the answer will be 0. No, this is not the case in this time. Okay, so del x by del x by y cap, the second term will be here. In the similar way this term will be here. Okay, in the similar way we have this term. Okay, so now what I want to say is that how to prove this. We will expand this term. Okay, so how we are going to expand this? First we will take the dot product of ax bx plus ay by, and the other term. Okay, and taking the gradient operator will be like this. So the simplest way we can prove it without tensor is proving LHS equal to RHS. Okay, so first of all we will operate this and expand this, and similarly we will take these individual terms and expand individually. There will be many terms that is going to cancel out, and finally the result will shows that LHS is going to equal to RHS. So I am not doing it right now, because it will take more time. Maybe I can derive it for the separate video. If you want me to derive it, then you can write it in the comment. Okay, so you should remember this identity. Next time I am going to write the formula for the divergence. Okay.